In this video, we're going to talk about how scientists find planets outside of our own solar system. So typically, you'll see these referred to as exoplanets. And sometimes you'll see them as extrasolar planets. So in this case, exo is referring to being on the outside, beyond, like the exoskeleton of an insect, and extrasolar, just outside of our solar system. So we have 4 different kinds of methods that we use. So we have the direct detection. And this is the method that we would use for our own solar system. If we were looking at Jupiter or Saturn, maybe we're looking at Mars, we use direct detection. This means that we're looking at the actual object itself and using some maybe visible light, or maybe we're looking at it in infrared or some other part of the spectrum. The other 3 that we also have Astrometrics. Make sure you guys can still see that. Let me move this over a little bit. We have the Doppler method. And we also have transits with the transit method. And these 3 methods, these are our indirect methods, where this one is our direct. Now, the reason that these are indirect is because we're looking at planets that are so far away that we don't have technology to see something that small that far away. But what we can see is the star that these planets are orbiting around. So we look at the behavior that the star has, and from that we can infer if it has something orbiting around it and a little bit of information about what that is. So let's start with astrometrics. So astro is just the word for star, and metrics, we're measuring something, like a meter stick. For astrometrics and Doppler, both these methods are using the tug that the planet orbiting the star is going to have. So let's go ahead, let's draw a little system here. Let's make a red star. And around this star is a planet, and the planet is orbiting that. So it's going around like this. Now we have to remember that gravity is not a one-way thing. So both of these objects, the planet and the star, are pulling on each other. And even though we often talk about the planet going around the star, what's actually going on is that they're both going around a center of mass. When one object is much, much larger than the other objects, then often that center of mass will be somewhere inside of the star, something like this. So this star here is also moving around this little center of mass. So it's moving back and forth, this little circle, and then the planet's going around it and around it and around it. So there's a lot of movement. In astrometrics, what we do is we look at the change in position that this star has. So it's going back and forth, and this may not be very much, but our eyes can't see it, but our sensors and our computers can. So we measure it going back and forth. And from that, we're able to figure out that something must be moving it. It's not just going to do that on its own. It has to do that in relationship to something else. So we can say, okay, well, something's orbiting it. It could be a planet like this, or it could be another star. And how we figure that out is how much movement's happening. The Doppler method is also looking at this, is taking into account that this movement is happening. But what it's doing is, instead of measuring the position of the star, it's looking at the light that we receive from the star. So let's say that we see the light is slightly redshifted. Then we know that the star is moving away from us. But if it's blue shifted, we know that it's moving towards us. So we can figure out what this little movement right here is based on the red shift and the blue shift. And from that, we can then go, okay, well, something again must be causing this motion to occur. So something has to be around it. These two methods, the Astrometrics and Doppler method, are very useful for finding planets with very large masses, or ones that are closer to their stars. However, we still have the transit method to talk about, and this one is better suited for smaller planets. It doesn't require that they be of large mass. And I said smaller, but I really do mean to say mass, because mass and size are not necessarily the same thing in these cases. So the transit method is the one that we have found the most planets through. So let's see how this works. Let's say we have a field of stars. So let's draw some stars here. Let's put some other colors in, because stars are many different colors, and we can learn lots of things like their temperature and age and all kinds of things like that just from whatever their color is. So yeah, maybe some blue ones in here too. And let's draw Earth. So we've got Earth. We're all the way over here on Earth. Get some ocean in there. Maybe a little bit of a continent. Oops. Let's get some actual color. So a continent here. And around the Earth, we have lots of satellites. And one of the satellites that we have up there right now is part of what's called the Kepler Mission. So let's draw this satellite. Has some solar panels. Okay. And this satellite is measuring this field of stars here. And what's happening is that each of these stars is giving off light in every direction, right? And so some of that light is coming, and let's look at this one. It's actually looking at all of them at once, but we'll just look at this one. And the light is coming right into the sensors in this satellite. Now we have one right now that's called the Kepler Mission. And this is named after a very famous astronomer, Johannes Kepler, who you may learn about because of Kepler's laws of planetary motion, which we use to help us calculate the orbits of planets and our spacecraft and all kinds of things. So we have the light coming into the sensor here. Now what it's looking for is, instead of looking for position and anything like that, it's not looking at the color. All it's looking at is how bright the light is that's coming. And it's looking and it's recording each of these and then looking for any change. So what we get out of this is we get a graph. Now the changes that we find are so tiny that our eyes don't see it, but these sensors can. So here on the Y, we've got light. And it doesn't matter what the unit is here because we're just looking for the difference. So let's just say this is 100%. We have 90%, okay. And then here we have time. Let's move this down so you can see it better. And again, the unit doesn't matter too much. It could be hours, days, anything. For us, let's just say, we're going to say we're using days. 9, 10. There we go. So let's say that on day 1, this is how bright the star is. And we look at it the next day, and it's about the same. There's not really a big change. Once again, it looks the same. And then we get to day 4, and all of a sudden we see this drop and it goes down. So what's going on? Day 5 goes back up, 6, 7, and on day 8, all of a sudden it goes back down. And so we start to see this pattern. So let's fill this in so we can see it more easily. So we see this dip happening. And we go, okay, well, why? This is saying that less light, it's not as bright as the night before. So how is that happening? So what we infer from this is that here, something must be getting between this star and our sensors. So something's getting in here, and we say that's probably a planet. And from looking at this pattern, we can figure out that it's quite regular. So, okay, so we have something that has a period, has an orbital period of 4 days. So, orbital period. Now, another word for this is its year. So the Earth has an orbital period of 365 days. That's how long it takes it to get around its sun. This hypothetical planet, that's going around this star, would have a year or an orbital period of 4 days. Now, there is one major disadvantage to this method, and that's that it only works if the planet is edge on to the Earth. So let's draw the Earth again here. So we've got the Earth, and let's put our star in an orange star this time. And, oh yeah, we have to get our satellite into, not quite as pretty as the other one, but you get the idea. And our satellite is watching. And we have a planet here. Now this planet's orbit has to go like this around the star, or in some other way that it's going to block it, right? It could be going like this. But the planet always has to come between us and the star so that the light can be blocked. If the planet's orbit is something like this, it's going around, then it's never going to block the light from this star to get to us. So we would have no way using the transit method to tell that there's a planet there. So in that case, if we were looking at a specific star and we really wanted to know if there was a planet there, we would be more likely to try and use one of these methods here. But that's going to be challenging if the planet that we're looking for isn't supermassive. These are our 4 methods, and hopefully in the coming years we'll develop even better technology which will allow us to use the direct method more often, and maybe we'll develop these other methods even further and continue to find other planets outside our solar system.